Hello, my name is David Jensen, and I'm going to spend a few minutes telling you about the work of my research group, the Knowledge Discovery Laboratory, and our work on computing for the common good. The Knowledge Discovery Laboratory studies principles, methods, and practices for learning causal models of complicated systems from observational and experimental data. We motivate and evaluate our work by also working on challenging applications, and I'm going to tell you about three specific examples. In the first application, we analyzed data about the entire US securities industry and how frequently individual brokers changed jobs. Among the things we discovered was that audits conducted by an industry regulatory organization actually caused brokers to leave the firm that was audited, and we were able to show that that was a causal dependence, not just a statistical association. In the second application, we constructed causal models from data about the performance of a database server. We examined performance data on specific queries and identified those parameter settings of the database software that cause specific queries to be processed more or less efficiently. And finally, in the third example, we're currently analyzing data about robotic control systems to explain why the robot takes specific actions and to explain the environmental conditions that cause the robot's navigation to be more or less competent. The laboratory's work focuses on causal models, so it's worth asking why that particular focus. Now, nearly all existing work in machine learning focuses on learning statistical associations rather than causal dependence. However, a wide variety of mission-critical applications require something more than mere associations can provide. Specifically, many applications require one or more of the following. First, many require reasoning about interventions. That is, we want to accurately reason about the effects of explicit actions rather than just what can be predicted given particular observations. Second, many applications require what we might call robust reasoning. That is, we want to be able to easily adapt existing models to changing environments without having to relearn the entire model. And finally, many applications require some form of explanation. That is, we want to automatically generate human understandable explanations of the model's inferences. All of these three things are obtainable with causal models and nearly impossible with mere statistical associations. Now, I've also mentioned the laboratory focuses on both experimental and observational data. Experiments are usually considered the gold standard for determining cause and effect, so why focus on observational data as well? Well, first, there's a question of feasibility. In many plausible scenarios, experimental data is nearly or completely impossible to obtain. For instance, you can't reasonably expect to conduct randomized controlled trials on the US economy. Second, even when you can run experiments, they're often expensive or costly in other ways. Third, even when you can run experiments, observational data is often plentiful, and it would seem wasteful not to attempt to use that data in some way. And finally, experiments are often artificial in one or more ways, whereas observational data is almost always generated under more realistic conditions. So for all of these reasons, we're interested in analyzing both experimental and observational data. By now, I hope I've convinced you that we're working in an interesting area, but where are we innovating? There have been decades of work in causal inference by highly capable and thoughtful researchers, and of course, we're building on that work, but we're doing so in a highly targeted way that we think offers the best chance for major innovations. Specifically, we're focused on developing new principles, methods, and practice to harness previously unexploited structure in observational data that allow us to infer more accurate and more useful causal models. I'll talk about our work in three related areas. First, in how relational and temporal structures can be used to better infer causal models. Second, how procedural structures can help us infer causal models. And finally, how compositional structures can aid causal inference. Now, some of our earliest work in causal inference examined how to use relational and temporal structures to aid causal inference. These sort of structures are common in social networks and organizational data, which often record relationships about, for instance, who works for whom. Software systems, particularly, say, computer networks or distributed systems, also have this kind of structure. And finally, many technological systems, such as data centers or building control systems, have this kind of relational and temporal structures. These sorts of relationships and how they change over time are vital for understanding causal dependencies. However, until our work, very few causal models explicitly represented and learned causal dependencies of this type. We've published a number of key papers in this area, and other researchers have built on that work. Another key finding of our work is that existing formalisms for representing causal models, specifically linear equations and causal graphical models, are overly constraining and cannot easily represent key features of many real causal systems. Recently, we've been exploring how new classes of causal models can be represented by probabilistic programs. These are procedural programming languages with probabilistic semantics and built-in inference methods. Now, these languages are particularly useful because they're substantially more expressive than classical causal models, and they also often provide more flexible and capable inference methods. Again, we've published several papers in this area and several more are on the way. Both of these two papers were published at the International Conference on Probabilistic Programming. Finally, we've recently been exploring how compositional structures can be used to improve causal inference. By compositional structure, we mean knowledge of how multiple objects combine to form other objects. For example, we see this kind of compositional structure in how school districts are composed of schools, and schools are composed of classrooms, and classrooms are composed of students and teachers. Traditionally, in statistics and machine learning, these kinds of compositional structures are sometimes seen as imperfections in the data. However, we show how this kind of compositional structure can be leveraged to make causal inference less biased and more effective. In particular, we use compositional structure to remove latent confounding, one of the most persistent and vexing, frankly, challenges of causal inference. Again, we've published several papers recently on this topic, including a paper at the last summer's International Conference on Machine Learning. I also want to point to some important applications of our more fundamental work that I've mentioned above on how we might apply this kind of work to interesting applications for the common good. Specifically, we've been applying our work on causal inference to two key projects that are aimed at making artificial intelligence models more transparent and more accountable. First, we've been applying our causal modeling work to explain the actions of artificial intelligence agents that have been constructed using deep reinforcement learning. Secondly, we've been doing similar work to assess the conditions under which deep models will be competent, that is, where they will act sensibly, and more importantly, where they won't act sensibly. This work has produced several interesting recent papers, including work at a recent conference on learning representations that critiqued the use of saliency maps in reinforcement learning. Saliency maps are a common method that purports to explain the inferences of deep models, but we show that much of that purported utility of saliency maps evaporates when they're rigorously tested. Finally, we're also working on a more overarching project to upgrade the way that the community evaluates its own research progress. Evaluation in causal inference is substantially more difficult than it is in conventional machine learning, because evaluating a causal model requires knowledge of the effects of intervention, and can't be easily evaluated with a simple holdout test. Specifically, our analysis has shown that existing evaluation methods are often unrealistic in several ways, and we've suggested and developed several more realistic and more effective ways to evaluate new and existing methods for inferring causal models. We've published, of course, several recent papers on this topic, and these papers are already having an impact on how others in the field are evaluating their newest systems. Thanks for your attention, and please feel free to contact me if you have questions about our work.